Another type of thermochemical equation that you might have to write out is a combustion equation. For example, you might see something like this. Here is the formula for acetone, which is a liquid. And they might say the enthalpy of combustion for that is minus 1790.4 kilojoules per mole. Now what does this mean? It means that you have some sort of a material here. This compound is a fuel in a fire. They're going to burn this. And when they burn a mole of it, this is how many kilojoules it releases. It releases 1790.4. Now sometimes when you look this up in tables, they might list it like this. Now why would they leave off the minus sign? Because they expect you to know that that little c means combustion, that you're burning it. And if you burn something, that releases heat. There's no such thing as a cold flame. So this cannot be positive. They'll leave the minus sign off though and expect you to put it in. They'll expect you to know that this has a minus sign because it releases heat, that it is what we called in another video an exothermic reaction. So delta HC is always negative. Whether they write it down or not for you, it's always going to be negative. Now let's write out the thermochemical equation for this. Think of them as giving you the thermochemical equation in a kind of a code here. If this is the fuel, here's a template for combustion reactions that you can use. You can take the fuel and react it with oxygen gas. And that's going to give you, all the carbon in the fuel is going to turn into carbon dioxide gas. And all of the hydrogen in the fuel is going to turn into water liquid. If there are other elements present, there can be other products. For example, if you have sulfur in the fuel, you can get SO2 gas. But let's talk about that later. All right, so here's your basic template for a combustion equation. Now what you have to do is put 1 mole of fuel into this equation. You're not allowed to change that. And that's because the delta H that they give you is per mole of fuel. So it's 1 mole of fuel. So let's write it down. C3H6O liquid is acetone plus O2 gas goes to CO2 gas plus H2O liquid. All right, it's not balanced. We have to have a 1 in front of this. That's the rule. So when I put a 1 in front of that, there's 3 carbons on this side. So I can fix it up by putting a 3 there. When I put a 1 here, there are 6 hydrogens on this side. So I can put a 3 there, right? And that'll make 6. Now I've got this side all nailed down. How many oxygens on this side? Well, let's see. There's 6 there and 3 more there. 6 and 3 is 9. So there have to be 9 total on both sides. Now this side has 1 already there. So that leaves 8 of them. So I get the 8 left like this. And there it is. And now I can write the enthalpy of combustion that I was given down as just a plain old delta H. Always will be negative for a combustion reaction when they have that little C there. Alright, one more thing that you might see when they show you this, and this goes also for the enthalpies of formation that we saw in the last video. They will sometimes put a little degree sign up there. What does that mean? Well, it's nothing that is going to affect your calculations in the rest of the chapter. What it means is under standard conditions, when they put that little circle there. Now, what do standard conditions mean? Well, it means that all gases at 1 atmosphere, all liquids and solids, under a pressure of 1 atmosphere, and all dissolved species, things, are at a concentration of 1 molar. So that's an abbreviation for that, all of that. It's telling you that. And there's nothing that you really do with that information. When we're working with groups of thermochemical equations, as we will shortly, either they all have to have the little degree sign or just, or none of them can have it. All right, let's do one more quick one. Suppose I have delta HC for carbon monoxide gas is minus 283.0 kilojoules. And now I want you to write a combustion equation out for that. All right, here's our fuel, carbon monoxide. The template says add oxygen to that, and all of the carbon in the fuel is going to turn into carbon dioxide. But there's no hydrogen in the fuel, so we don't get any water this time. So the combustion equation will just look like this. So let's balance it. If I've got a 1 in front of the CO, I'm going to have a 1 in front of this. And I only need to add 1 oxygen on, so I can put a half there. So a lot of times in these kind of equations, you're going to get fractional coefficients, which was something that we said people didn't really like before. But when you're doing thermochemistry, when you're doing this kind of work, when you're writing thermochemical equations, you got to keep a 1 in front of this. And so what you need to do is put a half in front of that to get things to balance. Now there are 2 oxygens on each side of this. So you can get this equation a couple different ways, right? Well, you can't really call this a formation equation for CO2. Why not? Why could I not say this is also the delta H of formation for CO2? It's not. That would be a good test question. Why isn't this the formation equation? Because according to the last video, your reactants have to be elements in their most stable form. What would the formation equation for CO2 look like? Well, you'd have to have carbon and oxygen on this side and put them in their most stable forms. Carbon's most stable form is graphite. Oxygen's is O2 gas. And you have to add them together and make sure it's balanced. It is. Delta H for that is quite a bit different. Let me see. Do I have it here in my table on the side here? Yeah, it's minus 393.5 kilojoules. So this is the heat of combustion for carbon monoxide, and it's a completely different number than the heat of formation for carbon dioxide. I want you to be able to write out formation equations and combustion equations. They are a smaller part of the calculations that we are about to do in the rest of the worksheet.